Hello there, my name is Charles Osfan Msipa. Welcome to another presentation on differentiation. In this case, we're going to focus on the differentiation of exponential function base e, in this case, natural base e. Actually, what I want to emphasize here is that we're going to deal with this function and we'll see later how it's going to give us a way of deriving derivatives of other exponential functions of arbitral base a. So we start here with the exponential function y is equal to f of x is equals to e to the power of x. First of all, I would like to, before I handle this derivative, I would like to emphasize here that let's take e like sine as a function. In your case, you're saying the function is the exponential function. Now, this part of the function, I would like to call it the argument of the function. That's the argument of the function. In this case, what I'm trying to emphasize here, now we've got a simple argument x, but sometimes we can have another function there. In the case we're dealing with a composite function of e and another function there. That function, again, was going to call it an argument of e. Let's say, for example, if we have y is equals to e to the power, let's say, sine of x squared. So now the leading function here will be e, because I'm saying y is equal to e. That is what I can call my leading function is e. Then e is acting on sine, and sine is acting on x squared. So we've got the composition of function, actually more than two functions involved. So then, now every time I'm saying e to x, then you must understand that e is to x. X is the argument of the exponential function. So let's derive this derivative from the first principle. So say f of x prime will be the limit as delta x approaches 0 of e to the power x plus delta x minus e to the power x divided by delta x. I hope everybody here sees that we are mimicking our incremental quotient, which was, let's say it was given as limit f of x plus delta x minus f of x over delta x. So here I've just written exactly this, but in terms of e. So then, applying our rules of exponents, now we can say this is equals to limit as delta x is approaching 0. What I'm going to do here, we're going to have a product here of e to the power of x by e to the power delta x minus e to the power x all over delta x. So simplifying further, you can see here that you have got a common factor e to the power of x, which actually does not depend on e. So we can write it here as e to the power of x multiplied by the limit as delta x approaches 0 of e to the power delta x minus 1 all over delta x. Maybe before we've seen this limit, or you haven't seen it, but if you haven't seen it, you can try this. This limit actually is going to tend to 1. So in other words here, we're going to have the answer being e to the power of x multiplied by 1. Now, when you're dealing with this function, I would like you to always not overlook the fact that e to the power of x is the inverse to ln x. So then I've written here as e to the power of x times 1. I'll leave this one as it is, but at the moment, I would like to remind you that 1 is actually equals to ln of e, because ln of e is the log base e of e. I think you can see this clearly from the properties of logarithms. But what we've got at the moment is that if we've got the function e to the power of x, the derivatives comes up exactly as the e to the power of x. And that, I think, should be very interesting. The function is e to the power of x, its derivative is e to the power of x. But at this stage, I'm sure that this is not very revealing because it looks like we haven't done anything. So I'm going to take another exponential function e to the power of x and try to reveal more facts about the differentiation. Let's say now we've got function y equals to e to the power of 2x. So you can see now what we have here. We've got function y, which is 2x, and another function y, e equals to e power x. So now when we now end up with y, e to the power 2x, we can see now that we are actually here. We are dealing with a composite function, composite of the two functions. Now, let's see now how we can get now y prime using the incremental quotient, limit of incremental quotient. So say limit as delta x is going to 0 of e to the power 2x plus delta x minus e to the power 2x all over delta x. Now, doing the same kind of manipulation we did before, we remove the brackets here and write this as a product. Then you've got limit as delta x is approaching 0 of e to x multiplied by e to the power 2 delta x minus e to x divided by delta x. Now what you saw previous is that we had an e to the power of x. The e to the power of x appeared again as a derivative. So let's see what's going to happen here. Now, factorizing again here, what we're going to have a limit as delta x is approaching 0 of e to the power 2x multiplied by e to the power 2 delta x minus 1 divided by delta x. Continuing this side, what we're going to have here, we're going to have following e to the power 2x multiplied by limit delta x, limit of e to the power 2 delta x minus 1 all over delta x. Now we have got to think a bit. We cannot just conclude about this limit without noting that the limit which is actually equals to 1 is the following. Limit as x going to 0 of e to the power of x minus 1 over x. This limit is equals to 1, but what we must note here is that the argument of e is x, denominator here is x, and here we've got x. But this is not what we have here. There we've got 2 delta x, we've got delta x there, delta x there. In other words, the rate at which the exponential function is going here is not the same as the rate at which delta x is approaching 0. So to make that similar to that kind of situation or compatible with this kind of situation, so we can conclude this limit, what we need to do, we need to accelerate this by 2 and then also multiply the denominator there by the numerator, by 2. And when we have done that, we also need to accelerate here by 2. So once we've got that now, we see that 2 does not depend on delta x here. So, but what we have in this case here, in these brackets, is an entity which is exactly similar, exactly like that, or that's a similar type of expression. So now if we let this tend to 0, so now we see that we've got some compatibility there, then we can conclude that this limit is equals to 1. So what happens now, what we're going to have now, we're going to have this being e to the power 2x multiplied by this 2 here, which doesn't depend delta x, so it's 2 times 1. So we say 2 times 1, which is limit. Again, I'm writing this like this, and recall again that 1 is equals to ln e. You will see later why I'm trying to emphasize on this. But what is important, what you can see here, before we saw that when we had e to the power of x, the e to the power of s came back as part of derivative and multiplied by 1. Now here we've got e to the power of 2x as part of derivative multiplied by the derivative argument multiplied by 1. Actually, at this point, we've arrived at a very, very important principle of differentiation. What we have here as y prime is a derivative from the function of the function y e to the power of x. So our function here is e to the power 2x. So what we have here, we've got e to the power 2x as the derivative of this function, but coming multiplied by 2. But you notice that 2 is actually the derivative of 2x with respect to x, which is going in, that is equals to 2. So what is being revealed here is that whenever you're differentiating the function, the function, we call upon the immediate derivative of the function as y e to the power of x2x. The immediate derivative is e to the power of 2x. But we've got to multiply by the derivative of the argument. So in summary, we're going to say whenever we're differentiating a function, we're going to call upon the derivative of the immediate function and multiply by the derivative argument. What do I mean by immediate function? Maybe not everybody will say it exactly like that, but we will arrive exactly at the same concept. What we're doing here, y, when we say y is equal to e. E is acting on another function. So in this case, I would call my exponential function the immediate function. The function 2x is the argument of my immediate function. So whenever I'm differentiating, I call upon the immediate derivative of my leading function and multiply by the derivative of the argument. At this point, I think you can now say you know how to differentiate an exponential function. Let's say we've got y is equals to e to the power cosine of x. So creating that hierarchy, I would say ln is the leading function. Actually, let me make it a bit more complicated. Say x squared here. And then cos is the argument of e. And x squared is the argument of cosine. So the leading function is the exponential function acting on sine and cosine acting on that. So following what we've just said before, I will say then the derivative of y, we saw that exponential function bounces back exactly as it is, retain the argument cos x squared, then multiplied by the derivative of argument, in this case the argument of e, which is cosine, then I'll say derivative of cosine, this is argument, then multiplied by, I'll just write d there to show that I'm saying derivative of that, multiplied by the derivative, in this case, of x squared. So in this case, the argument here, cos, is a function, it's got an argument, so I'll do it this way. So the derivative in this case is going to come up as e to the power cos x squared multiplied by derivative of cos, immediate derivative of cos is actually minus sine, and it will retain the argument. But then after differentiating that, it must be followed by the derivative of the argument. In this case, it's going to be 2x. Then we can now simplify this and write it as 2x minus 2x sine x squared e cosine x squared. So at this point, I hope I've given you an example which is clear. You can go back and view what you have done and try to do similar examples from your text. Others, for now, I would like to say thank you for listening.